Hello everyone, I'm going to do a short recording on the derivation of this formula for the arc length of a smooth curve defined over the interval from a to b. And its definition of a smooth curve is that the function is differentiable and moreover its first derivative is continuous over that interval. So it's a little bit more strict than just to say it's a differentiable function. All right, we're going to start out by looking at just an animation of the idea and the concept, and then we'll get to the derivation. So we have this red graph here. It's really just a graph of x squared from -1 to 2. We want to get the exact arc length of that curve. All right, what we're going to do is split the interval up. In this case, it would be from -1 to 2 into subintervals. And for each endpoint of the subinterval, look at the corresponding points on the graph and connect those by straight line segments. We know how to measure, compute the length of the distance between 2 points of a line segment. All right, and then that will allow us to approximate that exact arc length. And if we use more subintervals, we're going to get more and more points on the graph, and the sum of these lengths of these line segments is going to get closer and closer to the exact arc length of the curve. So that's the idea. I'm just going to play through the animation a couple of times here and use the slider. All right. Once you get so many points on there, it's hard to delineate between the points and the line segments and the actual curve itself. But that's the idea. All right, now let's get to the details of how to derive that formula. Okay, so again, we're talking about a smooth curve, again, differentiable, and its first derivative is continuous. Call those smooth curves. So first step, we're going to look at the interval AB, break it up into many subintervals. All right, and we're going to just label those subintervals. I'm going to draw that on the screen here now, but we're going to split that interval from A to B. Jumped a little bit on me there. All right, but we'll split the interval from A to B up into lots of pieces. The first one we're going to call X1. Second one, X2 and so forth. We're going to go all the way down the line, but we're going to focus our attention on just a general one, the ith subinterval, which is going to be going from x sub I to x sub I plus 1. All right, and then down to the last, or the nth one. So we break it up into n subintervals. All right, and then we're going to, for each one of those, we're going to look at the endpoints. All right, so we're going to take those endpoints, look at the corresponding functional values in those ordered pairs, and find the length of the line segment connecting those points. So we're going to have two ordered pairs. We're going to write out the distance formula for that. Just as a reminder, the distance formula is the square root of the sum of the squares of the distance differences between the x coordinates and the y coordinates. I have that written out here. So we take the difference in the x coordinates, square it, add on the difference in the y coordinates, square it, take the square root of that. That's just a consequence of the Pythagorean theorem. All right, so now we're going to focus our attention on the I subinterval. If we look at the I subinterval, our x coordinates are x sub I and x sub I plus 1. Our y coordinates are f of x sub I and f of x sub I plus 1. So we're treating these as, in the formula up above, as x1 and y1 and x sub 2 and y sub 2, all right, in the distance formula. So then we just get this result down here. All right, now what we want to do is get a better expression to work with here. It's going to turn out, it's going to be related to a definite integral, and to apply that, we're going to need to use the mean value theorem. All right, so just a quick reminder of what the mean value theorem says. It says over an interval, I'm just going to, this discussion, we'll just call the interval from C to D. Then if we have, I'm just going to use A and B. This A and B is not the same A and B as our problem. There's some number for a differentiable function, all right, over this closed interval from A to B. There's some number between, we're going to call that number C, and it's between A and B. Could be the endpoints, could be in the middle, such that the geometric interpretation is that the slope of the secant line is equal to the slope of the tangent line. at the point C. So the slope of the secant line over the from the endpoints of the interval, which would be f of b minus f of a over b minus a, right, is going to equal the slope of the tangent line at C. Okay, fine. We're going to apply that to the interval x sub I up to x sub I plus 1, that closed interval. So that's going to look like this. F of x sub I plus 1 minus f of x sub I, all divided by x sub I plus 1 minus f of or x sub I has got to equal the derivative of some point in between. I'm just going to call that x sub I star. So it's some number in the ith subinterval. All right, now this denominator, that's just the length of the subinterval. That's delta x. Okay, so multiplying both sides of this by delta x and just clear the fraction out, and that would allow us to rewrite this as the difference f of x sub I plus 1. All right, the numerator, that difference, will be equal to the derivative at that point in between the endpoints times delta x. All right, now we're going to leverage that, and we're going to take that and substitute that into the square root expression, which is the length of the line segment connecting these 2 points on the graph of the function. All right, so we're going to go put that in now. Okay, I'm just going to copy and paste this down here for simplicity's sake. All right, and then we're going to say, okay, that's going to be then equal to the square root of the, and also let's leverage this notation. Also, this is really delta x, so that's going to be delta x squared, and then we're going to put in what we just had. This is going to be equal to that difference of the function values will be the first derivative of f at some point in between f of x, or x sub I and x sub I plus 1 times delta x, and we got to remember that we're squaring that. All right, now from here, just a little bit of rewriting, and then the formula is going to kind of pop out of it after we do some addition. But we got to remember, when we square a product, we can square factor by factor. All right, so we're going to do that next. Just going to put this in brackets to emphasize it, and then we're going to have delta x squared. All right, and then we can realize that we have this common factor between these two terms of delta x squared. So we'll take that out. And when we do that, we're going to have delta x squared, and then we're going to be left with, well, this is really 1 times delta or x squared. So when we pull that out of the first term, we're left with 1. When the second term, we just get the derivative at that special point squared. All right, now we're going to square root factor by factor. When we square root the first expression, well, we can't do much, but just write it down. It's just the square root of 1 plus the derivative squared. But when we take the square root of delta x squared, we're just going to get delta x. That's a key observation, right? So applying the mean value theorem, we get some expression involving the derivative of the function and delta x. Okay, now that, remember, was the length of the first of the ith subinterval. All right, so that was what we called L sub I. All right, and now we're just going to put that in. So those lengths, all right, are going to be all right equal to, the arc length is going to be approximately equal to the sum of those lengths. All right, we can change this here to an equal sign, and now we can just put that expression in here. All right, so we're going to have in there the square root of 1 plus the derivative at our special value squared times delta x. All right, now this should hopefully look familiar to us as a Riemann sum of the integral of a function, and this is the function that's going to end up being the integrand. So what we're going to see in the end here when we do this, all right, taking limits, again, thinking about the animation I showed at the beginning, as we use more and more and more points, this approximation of the exact arc length is going to get us closer and closer to the exact arc length, and we're going to recover that in the limit. So we're going to have the limit as limit of the sum as I equals adding up from over all the subintervals, and we're adding up our formula here. Let's copy this down. That is going to turn into, and what we using again, this is the limit definition of the definite integral. The sum and the limit, roughly speaking, turn into the integral sign. The delta x becomes dx, and we get the rest of it as our integrand. So it's going to be 1 plus, whether you use parentheses or brackets, doesn't matter right here. I'm just going to continue to use brackets. The derivative, and notice we're going to write f prime of x squared. Okay, no x sub I anymore. Right, so that's the idea. And just again, what we did here, just to kind of, as an overview, we're trying to quantify this notion that if we partition the subinterval from A to B up into many pieces and look at each endpoint, for each subinterval, look at the endpoints and the corresponding point in the graph, connect those points by a straight line segment, and then compute the length of those line segments and add them all up, we're going to get closer and closer to the exact arc length. All right, and then in the limit, as we let n go to infinity, we're going to get the exact arc length. And this is the formula that comes out of that. All right, one key step, of course, is writing down that length of the ith line segment was applying the mean value theorem there. So it's another important place that the mean value theorem from differential calculus comes to play here. A little bit of rewriting, adding up and taking limits, we get the arc length formula.